Hello! Today we're going to tackle a fun and tricky algebra problem. Our goal is to find all the integer solutions to the equation x plus 2xy plus y equals 49. Now, this equation looks a bit unusual because of that 2xy term. It's not a linear equation, and it's not a quadratic in one variable. It's a special type of polynomial equation in two variables, x and y. So, how can we approach this? A common strategy for equations like this is to use a technique called factoring. Our objective is to manipulate the equation to look like a product of two binomials. In other words, we want to rewrite the entire left side as something times something else. If we can get that product to equal 49, it will simplify the problem significantly. Let's begin by rearranging the terms in our equation. Our equation is x plus 2xy plus y equals 49. Let's group the terms with x and y together. We can write it as 2xy plus x plus y equals 49. It's the same equation, just with the terms reordered. Now, our challenge is to factor this. The term 2xy tells us that our factors should look something like 2x plus and y plus. Let's try to set up the factors. Based on the 2xy term, a logical first guess for our binomials would be 2x plus a constant, let's call it a, times y plus a constant b. Let's FOIL this out to see what it gives us. FOIL, as you might remember, stands for first, outer, inner, last. So we get 2xy plus 2xb plus ay plus ab. We want this to be equal to our original left-hand side, which was 2xy plus x plus y. So we are setting 2xy plus 2xb plus ay plus ab equal to 2xy plus x plus y. The 2xy terms cancel out, leaving us with a much simpler equation. We need to solve 2xb plus ay plus ab equals x plus y. By comparing the coefficients of x and y on both sides, we can determine the values of a and b. Let's compare our expressions term by term. We are comparing 2xb plus ay to x plus y. Notice that our equation doesn't have a constant term, but the expanded factors have ab. This is a problem. It tells us that our direct factorization attempt wasn't quite right. Let's restart, but this time we'll manipulate the original equation first to make the factorization easier. This is a common and very powerful trick. Our equation is x plus 2xy plus y equals 49. The goal is still to factor it into something like x plus b, cy plus d. Let's see what happens if we double everything. Multiplying the entire equation by 2 gives us 2x plus 4xy plus 2y equals 98. Now, let's rearrange these terms, putting the 4xy first. We have 4xy plus 2x plus 2y equals 98. This looks promising. Notice the first two terms, 4xy plus 2x. They share a common factor of 2x. We can factor that out to get 2x times the quantity 2y plus 1 plus 2y equals 98. Now look closely at what's in the parenthesis, 2y plus 1, and the lonely 2y outside it. They are very similar. What if we could turn that 2y into a 2y plus 1? We can do this by adding 1 to the left side of the equation. To keep the equation balanced, we must also add 1 to the right side. This gives us 2x times 2y plus 1 plus 2y plus 1 equals 99. Look at that. We now have a common factor of 2y plus 1 in both terms on the left. We can factor that out. Factoring it out, we get the quantity 2x plus 1 times the quantity 2y plus 1 equals 99. We have successfully factored the equation. This is the key breakthrough. Let me repeat the steps because this is such an important trick. We multiplied by 2, rearranged, factored, and then added 1 to both sides. The result is a simple equation with two factors that equal 99. We've reached our factored form. The quantity, 2x plus 1, times the quantity, 2y plus 1, equals 99. 2x plus 1 equals 99. This means that 2x plus 1 and 2y plus 1 must be a pair of integers that multiply to give 99. So, our next step is to find all the integer pairs that are factors of 99. We need to consider both positive and negative factors. Let's list them. Positive pairs are 1 and 99, 3 and 33, 9 and 11, and the reverse of these. The negative pairs are -1 and -99, -3 and -33, and -9 and -11, and their reverses. In total, we have 16 factor pairs. This is a comprehensive list of all integer pairs whose product is 99. Each of these pairs represents a potential solution. Now, let's analyze the expressions themselves. Look at 2x plus 1 and 2y plus 1. The structure is 2 times any integer plus 1. Think about what kind of number this always results in. If x is an integer, then 2x is an even number, and an even number plus 1 is always an odd number. This means that both factors, 2x plus 1 and 2y plus 1, must be odd integers. This is a very important condition. We can now filter our list of factor pairs to find only the odd ones. Let's re-examine our list. The even factor pairs are those where both numbers are even, or one is odd and one is even. Neither of these can multiply to 99. Wait, let's look closer. A product of two integers is odd only if both integers are odd. In our list of factor pairs, are all the numbers odd? Yes, 99 is odd, and all of its factors, 1, 3, 9, 11, 33, 99 are odd. This means we don't need to filter anything out. Every pair we listed is a valid candidate for the factors of 99. We're almost there. We have our simplified equation, 2x plus 1, 2y plus 1 equals 99, and all the possible integer pairs. Let's take them one by one and solve for x and y. Let's start with the first positive pair, 199. This means 2x plus 1 equals 1, and 2y plus 1 equals 99. Solving the first equation, 2x equals 0, so x is 0. Solving the second, 2y equals 98, so y is 49. This gives us our first solution, 0, 49. Remember the reverse pair? 99, 1. This is just the same thing with x and y swapped. So x equals 49 and y equals 0. That's our second solution, 49, 0. Let's do another positive pair, 333. 2x plus 1 equals 3, which means 2x is 2, so x is 1. 2y plus 1 equals 33, which means 2y is 32, so y is 16. This gives us solution 1, 16. And the reverse, 33, gives us the solution 16, 1. And our next pair, 9, 11, yields the solution 4, 5. Again, the reverse, 11, 9, gives us 5, 4. Now for the negative pairs. Let's try -1, -99. 2x plus 1 equals -1, so 2x is -2, meaning x is -1. 2y plus 1 equals -99, so 2y is -100, meaning y is -50. Our solution is -1, -50. And the reverse, -99, -1, gives us the solution -50, -1. Let's try the next negative pair, -3, -33. 2x plus 1 equals -3, so 2x is -4, meaning x is -2. 2y plus 1 equals -33, so 2y is -34, meaning y is -17. This solution is -2, -17. And the reverse, -33, -3, gives us 17, -2. Finally, the last negative pair, -9, -11. 2x plus 1 equals -9, so 2x is -10, meaning x is -5. 2y plus 1 equals -11, so 2y is -12, meaning y is -6. Our final solution is -5, -6. And the reverse, -11, -9, gives us -6, -5. So, let's list out all the integer solutions we found for the equation x plus 2xy plus y equals 49. We have 8 unique pairs. Let's quickly check one of them, for example, 4, 5. Substitute x equals 4 and y equals 5 into the original equation. We get 4 plus 2 times 4 times 5 plus 5. This simplifies to 4 plus 40 plus 5, which equals 49. It works. The solution is correct. Just to recap the main strategy, we used a clever trick of multiplying by a constant and adding a term to transform the original equation into a factored form. This made it possible to find all integer solutions. This technique is often called Simon's favorite factoring trick, and it's a great tool to have in your mathematical arsenal. Thank you for watching.